Coming to the concept, actually we have this concept is state feedback controller design. Now, how to design a state feedback controller, that I would like to present now. To find the gain matrix K, there are three types of methods over there. But I'm going to explain only two methods. The last method is Ackermann's formula. That is somewhat difficult to compare it to these two methods. So that to design a state feedback, let us coming to the previous diagram. I'm going to design a state feedback controller using pole placement technique. What is pole placement? Let us consider any closed loop system with a desired closed loop poles. Based on the location of the poles, we can design one feedback respective to a gain constant K, that is called a state feedback. Suppose if you take any S-plane, let two poles are designed the left half of the S-plane. Let the two poles is minus S1, the first pole. This is minus S2. Let us assume that two poles are located in the left side of the S-plane. For what value of poles, the value of K should be designed. That is, it is two poles means second order. Therefore, K1 and K2 values could be designed based on these two poles. Suppose if the poles are located in the right side of the S-plane, again, what is the value of K? The given matrix we have to find, that is K1 and K2. This is what we are going to see in the present class, how to design a desired polynomial value of K gain with respect to closed loop poles. That is called a pole placement. That means based on the location of the poles, how the value of K gain constant K can be designed. I'm going to explain with a small example. That means I'm going to explain this diagram. So as earlier I have said, this is a block diagrammatic representation for the state equation without state feedback. This is for state equation x dot is equal to, you already know that x dot is equal to ax. This is for ax plus b into u. And output equation y is equal to cx. This is what we have discussed in the previous example, previous class, cx plus b into u. So this red color, the block diagram corresponding to the original state equation as well as output equation block diagram. Now coming to the next one feedback which is connected from the state variable, that is from the x, with the gain constant K respected to input over here, where R is a reference input, it is a system input. Then this diagrammatic representation includes, state feedback. This is called a state feedback. When I connect state feedback of the system, again, this equation can be modified as the new state model can be replaced by, again, x dot is equal to, the matrix A can be modified as A minus B is multiplied with the gain matrix K, x plus B into the reference input R. And output matrix, there is no change, y is equal to again Cx plus there is no change in the output. Now compare with the red mark and blue mark equations. What is the changes in the matrix A? Here, before connecting the state feedback, the matrix A is original matrix from the second order system. But when you connect the state feedback, matrix A can be replaced by A minus B into K. Look at this one. This is the main comparison. That means based on value of K, the entire eigenvalues of the system can be placed, or roots of the polynomial can be placed either left side of the S-plane or right side of the S-plane. so that we can decide stability of the system. That is what we are going to explain in this. Right? For stable system, how to calculate the value of gain constant K and how to design a state feedback control. So actually, this process, they have given closed loop poles. Here we are going to find the value of gain. That's the matrix gain constant K with respect to the given closed loop poles. So to find or to design state feedback controller, sometimes we can call this a state feedback controller. That's the gain constant. Because based on the value of K, the poles location can be changed. That is SFC, state feedback controller. So based on given poles, closed loop poles they can give. Based on those poles, how the value of gain constant is going to be designed. This is what we are going to see in the present class. Let us coming to that one. There are three methods to find that gain constant K for state feedback controller. On the three methods, I will discuss only two methods. First method is Gauss-Murray formula. What is the Gauss-Murray formula? That I can explain. The next method is method number 2 is direct substitution method. So what is the process in the direct substitution method? With an example, I can explain. Among these two methods, I can go with the substitution method. This formula is also, this method is also somewhat difficult. But second method, that is direct substitution method, is applicable only for if the order of the system is less than or equal to 3. So that second method is not applicable for, applicable means it is okay, but somewhat difficult. So that we cannot go for the second method if the order is more than 3. So that I can explain both the methods, but I can go with second method problems only. Okay. Let us coming to the first method. What is the method to find the value of matrix? Okay. This is what we are going to see for the given closed loop poles. Let us coming to this one. Find the coefficients of the open loop characteristic polynomial. Delta of S is equal to S power n plus alpha 1 into S power n plus 1 plus and so on plus alpha n. What is the coefficients of the open loop characteristic polynomial? And this characteristics open loop polynomial we can obtain from the state equation. Because we already know that what is the state equation there. From that state equation, we have to find the polynomial. Next one, from the controllability matrices, we have to verify or we have to find one matrix with respect to inverse, which is called model matrix. This is note the inverse. What is this EVA? Generally, this is a control matrix, controllability matrix. Sometimes in the previous class, I have explained one composite matrix which is called QC. So there is a formula to find the controllability of the matrix. What is that matrix? B. The next matrix will be next row element, next column will be AB. Next column element will be A square into B, and so on like this. This matrix is called controllability matrix. So here is going to represent with a different letter. So I'm going to take it as E or C, whatever it is. So E is equal to B, A, B, and so on, A power n minus 1 into B, where E bar is nothing but inverse of the given matrix. So what is E bar? This is a matrix and with respect to minus 1. What is 1? What is alpha 1? What is alpha 2? And so on like this. 0, 1, alpha 1, 0, 0, 1, and so on like this. Now, this matrix is also called model matrix. This matrix is also called model matrix inverse. Generally, this matrix concept will become at the time of canonical form. That's to check the controllability. There are two methods we have discussed. That is Kalman's test and Gilbert's method. When you go through the Gilbert's method, there you can obtain this Kalman's test. There you can get this answer. So what is 1? and what is alpha 1, what is alpha 2. Before going to that, we have to find one characteristic polynomial from the given system, that is delta of s is equal to s power n plus alpha 1 into s power n minus 1 plus and so on plus alpha 1. Look at this polynomial. This polynomial we can obtain from the given state equation that I can explain with an example. There you can understand. Okay. So what is that polynomial? We have to go through that. So what is alpha 1? Alpha 1 is nothing but coefficient of s power n. What is alpha 2? Alpha 2 is coefficient of s power n minus 2. So maximum the system orders to be third order only, not for the second order. So generally this matrix would be E bar is equal. It should be like this. So that you have to remember this matrix every time, no need to find. The first element would be 1. The next element would be alpha 1. Next element would be alpha 2. What is the next row element? 0, 1, alpha 1. What is the next row element? 0, 0, 1. So you have to remember this matrix. If you take it is inverse, there you can get this matrix. Next, select the coefficients of the desired closed loop characteristic of polynomial delta k of s, that is s power n plus alpha 1 bar. If alpha 1, alpha 2 confusion ayyapanite, let this is a1 or a2, whatever it is. I'm going to take this is a1. Let us assume that a1 into s power n plus 1 plus a2 into s power n minus 2 plus and so on like this, a power a sub x. Yeah. And build the state feedback gain coordinates. Let us coming to this one. What is the difference between first polynomial and the second polynomial? The first polynomial we can obtain from the open loop characteristic polynomial, that is from the state equation. What is the state equation? We already know that x dot is equal to ax plus x dot is equal to ax plus b. From this we can obtain the polynomial. What is the polynomial? Already said it is a characteristic polynomial, therefore si minus a mod is equal to 0. So if we do this one, we'll get one polynomial. Let the polynomial is this one, delta of s, that equation 1. So what is decide closed loop characteristic polynomial? Very, very important. This closed loop characteristic polynomial we can obtain from the closed loop poles where they can give. These closed loop poles will be given by the problem because they have given closed loop poles. For the given closed loop poles, how you can design a state feedback controller, that is called K. This is what we are going to explore. So suppose if they give 3 poles, let the 3 pole values S1 is equal to minus 1. Let us assume. S2 is equal to, this is minus 2. Let us assume. And one more pole he has given, S3 is equal to minus 3. Let us assume that. Now, what is the polynomial over here? I can write this is like s plus 1, the first one. What is the second one? Second factor, that is s is equal to minus 2. Therefore, I can write this is equal to s plus 2. What is the third one? S is equal to minus 3. Therefore, I can write s plus. Let us assume that. Now, multiply 3 factors. If I multiply 3 factors, let us consider if I get like this s cube plus, let some coefficient, next coefficient is a1 into s square. Let us assume that. The next coefficient would be a2 into s plus. The next coefficient would be a3 is equal to 0. So this is a polynomial of the desired characteristic polynomial. Desired closed loop polynomial we can obtain for the given poles. Addition poles ki polynomial calculate cheste, that is called a closed loop desired poles. That's a closed loop desired characteristic equation. Let the characteristic coefficients are a1, a2, a3, and so on an. So therefore, we have 2 characteristic polynomial. First one is from state equation, that is mod Si minus A is equal to 0. There you can get one polynomial equation. And from the given closed loop poles, then you can get one more polynomial, that is called closed loop characteristic polynomial from the poles. Now, the value of k bar I am going to write over here. K bar is equal to, there is a one formula to find the matrix. What is k bar? So k bar is equal to, first one is alpha 1 bar minus alpha 1. Here alpha 1 bar, alpha 2 bar I am going to take as A1, A2 and A. Therefore, I can take this as, the first coefficient is A1 minus alpha 1. This is A2. And so on. This is AN minus alpha 1. This is K bar matrix. Now, finally, the state feedback gain matrix we can calculate with this formula, that is K is equal to, I can write K bar, that is already found in this equation, into E bar, because E bar is already calculated over here. Next one is E inverse. What is E inverse? Because here already from the point number 2, we found matrix E, that is a controllability matrix. Then if you find the inverse of that matrix, I will get total K matrix gain. So this is a method one to design a state feedback controller using method one. This is somewhat difficult, but this also to be easy if you know the process. So what is the process? Once again, I'm going to explain. First, we need to find the characteristic polynomial for the given state equation using this Sa minus A, mod Sa minus A is equal to 0. What is the next one? Find the controllability matrix from the Kalman's method. So that what is the controllability matrix? What's the second one? From the controllability matrices, we have to find out E bar matrix. What is E bar? E bar is one standard formula. Actually, it is not a formula. This will comes under model matrix. If you go through the Jordan canonical form, that is controllability testing Jordan canonical form by some other method, there you can get this matrix format. Matrix format make already need two methods, Kalman's test and Gilbert's method. If you go through the Kalman's test, if you go through the Gilbert's test, there you can understand this matrix. So, మనకు maximum అడిగేది third order system వరకే అడుగుతాడు కాబట్టి better remember for this one. 1 alpha 1 alpha 2, 0 1 alpha 1, 0 0 1. Now, what is alpha 1 alpha 2? We have to calculate this polynomial from the open loop polynomial. There we can get, because this polynomial we can obtain from the lambda Si, that is from the characteristic equation Si minus A is equal to. So this polynomial we can obtain from this equation. If you know the polynomial values, then you can find this matrix with respect to inverse. There you can get E bar matrix. Now select the coefficients of the closed loop polynomial. That is, for the, if it is third order system, he can give 3 poles. If it is second order system, he can give 2 poles. If it is fourth order system, they can give 4 poles. So suppose if they give 3 poles, then based on 3 poles, we have to find one polynomial. That is, by multiplying all the factors in the polynomial, I will get one more extra polynomial. That is called a closed loop polynomial. That is called closed loop polynomial. Let the closed loop polynomial coefficients are should to be, what are the coefficients of the polynomial? That this is A1. This is A1. The next coefficient would be A2. The next coefficient would be A3. And so on up to A. What is K bar? K bar is equal to subtraction of both the polynomial values. Let if suppose if it is a 3 by 3 system, let the polynomial values, I'm going to take a small example. Suppose if you have s cube plus ps square, let us assume that I'm going to take small example. Plus I have 4s plus 5 is equal to 0. If I get The polynomial is like this. Let equation. Now, what is E? This we can find. This is E is equal to, it is a third order system. Therefore, I will get only B. The next column would be A into B. The next column would be square into B. So this is a 3 by 3 matrix. Now, what is matrix of E bar? E bar is equal to, I can find. First one is 1. What is alpha 1? What is alpha 2? Coming from equation, what is alpha 1? That is S square coefficient. What is alpha 2? S coefficient. Like this. Next, what is the next row element? 0, 1, alpha 1. Therefore, 0, 1. What is alpha 1? 3. Next, what is the value? 0, 0, 1. This is a E bar matrix. And we have to find out its inverse. E bar is nothing but obtained matrix with respect to inverse. This is E bar matrix. Now, what is a closed loop polynomial? This closed loop polynomial we can obtain from the given poles. Let there are 3 poles as given. Let the 3 poles would be -1, -2, -3. Let us assume that I can write this is like S plus 1, that is 1 pole, is multiplied with the second pole because I am going to find the polynomial S plus 2. Let us assume that. What is the third pole? S plus. Now multiply these 3 poles, I will get this is like S square S. So 1 and 2, and it gives 3S plus 2 is multiplied with again S plus 3. What is the value now? So S cube, okay, S. Next one is 3S square, and here is already 1S square. Therefore, it gives 4S square S. Next one is 2S plus already 3S. Therefore, I can take this is 2S plus again we do the multiplication S2 plus sorry standard multiplication, then only you can understand. So only there are 2 methods. Now let us multiply both the factors. I will give first one is S cube plus 3S square plus 2S. Okay. Again multiply by 3S square plus 6S, sorry, 9S plus 6. What is the polynomial value? S cube plus 3S square plus 3S square means 6S square plus 3S plus 9S means 11S plus 6. Let us assume, let equation number. Let the polynomial coefficients, the first, leave that to higher degree polynomial. Afterwards, we have to consider this is A1, this is A2, and this is A3. This is A3. Let us coming to our. So what is A1? What is A2? Like this. So this is A1, A2. Here it is A3. Now what is the value of K bar? So K bar is equal to directly I can write A1 minus alpha 1. Where alpha 1 is nothing but what? 3. What is A1? 6. 6 minus 3 is 3. Next, what is A2? A2 means 11. So 11 minus what will be the value here? 4. 11 minus 4 means 7. What is the next one? A3, 6. 6 minus 5. This is K bar matrix. So K bar matrix is there, E bar matrix is there, and E also to be there. And what is the value of gain matrix? K is equal to A bar is multiplied with E bar and is multiplied with E inverse. Because if you find the controllability matrix E, and we need to find the inverse matrix also. Okay. So this is a whole process to find gain matrix K for the given any state equation on the output equation. So this closed loop poles they can give. Based on that, we have to determine this gain matrix K. So I can show one problem, then you can understand. Before going to take the second test, second one. Look at this one. Consider the system defined by x dot is equal to ax plus b. The matrix A is given, the matrix B is given. Because to design any state feedback controller, there is no need of matrix C. We have to check only controllability. Therefore, AB matrix are enough. Using the state feedback control, using the state feedback control, that is E is equal to minus kx. Today's result we have closed loop poles. Already said that closed loop poles they can give s is equal to minus 1 plus or minus j to s is equal to minus 10. Determine or design the state feedback gain matrix K. To go to the previous method, now look at this method. As earlier I said. So using method 1, we can find the matrix K. I hope you understand. So what is the first matrix? What is the first polynomial? This polynomial we can obtain from the state equation. What is the state equation over there? Let us connect it. X dot is equal to x plus b. A matrix is given, B matrix is given. Therefore, we already know that the characteristic polynomial is Si minus A not is equal to 0. Si minus A not is equal to 0. So next, what is the process? Look at this one. If I take this as Si, matrix A is a 3 by 3 matrix. Therefore, S is multiplied with, I can write identity matrix 1, 0, 0, 0, 1, 0. The next value would be 0, 0, 1, minus. What is the matrix A? A would be 0, 1, 0, 0, 0, 1, minus 1, minus 5, 6. Not is equal to 0. Suppose it is a 3 by 3 matrix, therefore I will get that some coefficients SQ plus, I'm going to take small example, therefore I can write SQ plus 5s square plus 8s plus 9 is equal to 0. Let us assume this is equation 1 we can obtain from this equation 1. So that is for the first point. Coming to this one. For the first one, I got the expression is like this. This is for the first point. What is the second point says? This method from the controllability matrices, we have to find the matrix. What is the matrix? That is coming to over. Matrix E should be, we have to find. It is a third order system. Therefore, the matrix E should be only we have 3 elements. That is, the first column is A. Next column would be A into B. The next column would be A square into B. This is E. So we already know that there is a matrix A and matrix B. We already know that. Therefore, it is very easy to find second point also. Right. What is the third point? That is E bar. Now, how to find the E bar matrix? Look at this one. I can write over here. E bar is equal to, what is the formula? So what are the polynomial coefficients here? It is alpha 1, alpha 2, alpha 3. So what is the formula there? There only up to alpha 2 only. So let us coming to over here. 1. What is alpha 1? It is 5. What is alpha 2? It is 8. Again 0, 1, 5. The next one is 0, 0. This is matrix E bar. And if we take inverse, we can take E bar. This is matrix E bar. So matrix E bar is also over. What is the third one? Select the coefficients of the desired closed loop characteristic polynomial. What is the closed loop characteristic polynomial? Look at this one. S is equal to -1 plus or minus j2, S is equal to -10. There are 3 poles. So therefore I can write this is S is equal to -1 plus or minus j2 means S plus 1 minus j2 is one type of pole, and there is one more pole, S plus 1 plus j2 plus j2, and is multiplied with what is the third pole? S is equal to -10. Therefore I can write S plus 10 is equal to 0. Suppose if you multiply these factors, if I get like this, S cube plus some 8 S square plus 12s. Let us assume that. I'm going to write only just for the understanding purpose. And 13 is equal to 0. That this is equation number 2. This is obtained from the closed loop poles. This is obtained from the open loop poles. This open loop pole characteristic equation we can get from the state equation. And this characteristic polynomial, it's a closed loop polynomial we can obtain from the closed loop poles, where they can give. Now, what is A1, A2, and A2, A3 like this? Let A1 value is 8, A2 is equal to how much? 12, and A3 is equal to 13. So, coming to the method number, point number 3, so which is already calculated. What is K bar? It is difference of both the polynomial coefficients. Let us know the K bar next. What is K bar? I can write over here. So, K bar is equal to, what is first one? A1 minus alpha 1. That means 8 minus 5. That is the 3. Next one, 12 minus 8. What is next one? 13 minus 9. Should be. This is K value. So what is K value? So K value is nothing but multiple of K bar, multiple of E bar, multiple of E inverse. So if you multiply the 3 matrices, that is K bar is multiplied with E bar. So E bar matrix is over there and is multiplied with E inverse. E matrix is there because based on the controllability matrix. This is a matrix E. To find its inverse, that is E inverse. And if you multiply 3 matrices, you can obtain the matrix K. So this is a process method to find or to design closed loop control state feedback. That's a state feedback controller design. I hope you understand. Go through the Nagar Kani textbook or any other textbook. You have 3 methods. The first method is a Basura method that I have explained now. The second method I will explain in the next class. That's a direct substitution method. And this Basura method is applicable to all the system. The order is more than 3. But comparative to this method, method number 2, direct substitution method is very, very easy. That I can explain in the next class, how to find the value of K in K. But if the system order is more than 3, I think first method is a good method. That is obtaining the coefficients of the open loop polynomial for the state equation, controllability matrix, model matrix, closed loop characteristic polynomial. Also, finally, you have to design a state feedback. I can share the PPT. There you can understand concepts more easy. So I will go with the example in the next class. When after completion of both the methods, I can go with the direct substitution method. The examination is also everyone. If the system order is less than or equal to 3 లేదా అంతకన్నా తక్కువ ఉంటే మాత్రం better go with the direct substitution method. Don't go for this Gauss-Bura method. That is Gauss-Bura formula method, because there are a lot of calculations are there. Inverse matrices like this. Better if they ask find inverse matrix, we are in the process. So you want to find the inverse matrix. So don't go to the standard method to find the inverse matrix. It takes more time. So use calculator. If the matrix A is there, then its inverse directly you can find from the calculator. Just go through the calculator method. Calculator lone third order system ki 3/3 matrix ki inverse at a time calculate cheyachu. Exam lo ganaka 3/3 matrix ki inverse calculate cheyadam as per the procedure prakaram ellarante meeku time saripod. Okay, so please go through the calculator. There you can find or you can get the total information. Right, Swati.
Yes, sir.
Please absent is not present is not చేసుకున్నావా?
చేస్తున్నాను.
Right, నాకు WhatsApp పెట్టమ్మా.
సరే.
Thank you guys. Thank you so much. I'll discuss in the next class.